Good morning, everybody. Sorry for being sick on Wednesday, but what can I do? I'm not sick anymore, so you will not be infected. Maybe you wanted to be infected, but I'm sorry. Anyway, I don't know if you're like my kids who want some good excuse to quit, to stay at home and not to go to school. Anyway, so today we're going to talk about Bose-Einstein condensation. In particular, we have discussed last time that if we have a system that satisfies Bose-Einstein statistics, then the number of particles, the occupation of a mode with momentum p is going to be given by 1 over e to the beta epsilon p minus mu minus 1, not plus 1, unlike Fermi's. And this minus 1 is forcing the chemical potential mu to be negative, or to be, if epsilon p, it depends on the dispersion, but in any case it has to be smaller than the bottom of the dispersion. Okay? So if we assume a standard dispersion like p squared over 2m, then it has to be negative. It's clear? So now, let us play the following game. Let us try. So we have a gas with n particles, and we fix temperature, and let us find, as a function of temperature, the chemical potential in such a way as to fix this number of particles, right? So now I'm going to solve this problem of fixing the chemical potential as a function of number of particles and temperature in the following way. In principle, I would have to solve this equation. Right? Where P is a set of momenta which is, discrete, and so in general is going to be 2 pi nx over Lx, 2 pi ny over Ly, 2 pi nz over Lz if I'm in 3 dimensions, where n alpha belongs to integers, actually to z. Now, however, so what we usually do when we want to estimate this integral is, okay, we assume that the temperature is sufficiently large as compared to the gap in the spectrum, right? So these levels are going to, since the momenta are discrete, there is going to be a gap, some small gaps in the spectrum. Also, the spectrum is going to be discrete, even if we take the dispersion epsilon p to p squared over 2m. But we neglect this discreteness when we pass to the continuum limit, right? So when we pass to the continuum limit, in practice we're saying we don't care about this discreteness. We assume that temperature is so large that this discreteness is not going to be resolved. So in practice we say that this is equal, or approximately equal to, v over h cubed integral dp 3 1 over e to the beta epsilon p minus mu minus 1. Okay, this is the passage to the continuum limit. So let me frame this stuff in a green box, just not to get confused. All right. And now, how do we rewrite this? Well, we pass to spherical coordinates, v over h cubed. So we have integral between 0 and plus infinity dp p squared 1 over e to the beta epsilon p minus mu minus 1 times 4 pi, right? 4 pi is the solid angle. And now, I can rewrite this, I can make a change of variables. So notice that, so let's make another green box down here. Notice that if you have epsilon p equal to p squared over 2m, then d epsilon is equal to p over m dp, right? Or, in other words, you can write it as this, you can see it as square root of 2 epsilon over m dp. So this tells you, in practice, that you can rewrite this as 4 pi v over h cubed. Then you have integral between 0 and plus infinity. D epsilon times square root of m over 2 epsilon. And then p squared is 2m times epsilon, divided by e to the beta epsilon minus mu minus 1. Okay? So now you do all the simplifications you have to do, and what you get at the end, you can go to the next page, is that this is equal to let me write it. Well, it's 4 pi v over h cubed. Then you have m to the power 3/2 square root of 2, and then integral d epsilon square root of epsilon 1 over e to the beta epsilon minus mu minus 1. Alright, so we can rewrite this is the way we usually write it, as integral 0 plus infinity d epsilon g of epsilon 1 over e to the beta epsilon minus mu minus 1, where g of epsilon is called the density of states. And is equal, for this particular case of a free gas in 3 dimensions, is equal to v and 3/2, and then you have square root of 2 pi squared h bar cubed square root of epsilon. Okay? Another question is, how do we calculate this integral? So, well, it's not easy. I mean, in principle, what you will have to do is to figure out solutions to this equation as a function of temperature, fixing, so this should be equal to n. You fix n, you fix the temperature, and you should find mu in this equation that is rather complicated.
So I can see, is it written h bar cubed or h cubed?
H bar cubed. So I absorbed all the factors of pi into h bar. Alright, so now let me graphically tell you what happens for this solution. So as I told you last time in passing, so if you think about the chemical potential versus temperature, so if you try to find a solution of this equation at very high temperature, so at high temperatures you will find it, and you will find some negative chemical potential that grows and tends towards 0 as the temperature decreases. And then eventually, in 3 dimensions, there is a point, there is a peculiar temperature at which the chemical potential goes to 0. Now, when the chemical potential reaches 0, then you understand that something strange is happening, because when the chemical potential is reaching zero, in principle, if you would lower even more the temperature and try to solve this equation, you would find positive solutions, which doesn't make any sense, right? So we will have to think carefully about what happens when the chemical potential reaches zero. But let us first find what is the critical temperature at which the chemical potential hits zero. And then we discuss the physics of what is happening at that critical temperature, okay? So, in order to find that critical temperature, we just have to solve this equation. We just have to find the temperature at which the integral between 0 and plus infinity d epsilon, g of epsilon, 1 over e to the beta epsilon minus 1 is equal to n, right? So this is the definition of critical temperature. So in order to solve this equation, let's make a change of variables. Let's call, so let me write it here, beta epsilon equal to x, and then this integral can be written as follows. It's going to be some constant. The constant is essentially this, okay, divided by beta to the power 3/2 times the integral between 0 and plus infinity dx x square root of x over e to the x minus 1. Now, the important thing to look for in this integral is that it's convergent. It's a convergent integral. It's obviously convergent for large x because it's exponentially decaying, but it's also obviously convergent at small x because you see that it's growing as 1 over square root of x, which is an integrable divergence. Okay? And in particular, this integral can be calculated exactly. It's just, well, I'll write the result. If you don't believe me, use the Mathematica and you will find it. Or if you don't believe Mathematica, go to the library. There's a book by Abramovitz, Stegan, or another one by Kratzstein, and whatever. If you don't know these books, spend some time in the library. And you will find also there this integral. So anyway, the solution is c over beta to the power 3/2 times the zeta function 3/2, gamma function 3/2. It's a product of a zeta times a gamma function. Zeta is the Riemann zeta function. It's a beautiful function. You should all study it. I mean, it's really very nice, but I don't have time to spend on this. Alright, so this is the result. So now beta is 1 over kBt. Kb is equal to 1 for me. And therefore we find that the critical temperature, Tc, is equal to n to the power 2/3 divided by c times gamma 3/2 zeta 3/2 to the power 2/3. So this is the critical temperature for a three-dimensional gas of free particles, bosonic particles, at which the chemical potential hits zero. Now what happens when the chemical potential hits zero? So if we have a gas of free particles, the dispersion is p squared over 2m. So which means that we have a mode with p equal to 0, which has zero energy, right? P squared over 2m. Now, what is happening when the chemical potential hits 0 is that in principle, the occupation of this mode is blowing up to infinity, right? So think about this. You see e to the beta epsilon p minus 1, you see that this diverges. So if you plug in 1 over e to the beta p squared over 2m minus 1, you see that if the chemical potential is 0, at small p, this is the divergent function. So at p equals 0, blows up to infinity. Now, this does not make any physical sense. You cannot have an occupation of a mode that blows up to infinity. It's an artifact of the fact that we took the continuum limit. So, if this function blows up to infinity, but the singularity is integrable, then you can still get a convergent integral. But you should think about the fact that we are not coming in a real system. We don't have the continuum limit. We have a discrete set of modes. Okay? So the only thing we're saying is that as the temperature decreases and decreases and decreases, the lowest energy mode gets an occupation that is higher and higher and higher. Right? At some point, the system is not able to allocate particles anymore in thermally occupied states. So below this critical temperature, what happens is that what you cannot put in thermally excited states, you put in the ground state and stays there. Okay? In other words, what happens at higher temperatures, so let me put it here, at higher T, at lower T, sorry, not at higher, at lower T, smaller than Tc, the chemical potential stays equal to 0. It cannot grow higher. So mu is equal to 0. It cannot be higher than 0. And then what happens is the following. If you compute the number of particles in excited states, which is equal to the integral dp, well, it's better, we already did the calculation. It's going to be equal to integral d epsilon g of epsilon 1 over e to the beta epsilon minus 1. This number of particles is smaller than n. Right? The number of particles that you can put in excited states is smaller than n. And the difference is all in the ground state. Now, you might say, well, you're cheating us. So I'm not cheating. What? I'm not cheating. This is a phenomenon that is observed experimentally. Right? It was observed the first time when I was a student. So it was 95 roughly, when I was a master's student like you. So a number of years ago. Unfortunately, I'm old, but older than you. Not old. But it's something that is observed. Now, it's true that what I'm saying, the reasoning I'm making here does not tell you where you put this difference of particles. So you put them in the ground state because you have to decrease the free energy, right? You have no other choice. But in principle, there are some systems in which you can create more complicated condensates. They are called fragmented condensates, in which you put a certain number of particles in one state, another one in another state, and another one in another state, and so on and so forth. These are extra complications. Let's leave them aside. But for the simplest possible systems, you just put them all in the ground state. Okay? Yes.
The fact that mu cannot go past 0,
yes,
we got it from the dispersion we also did.
Well, mu cannot go past 0 for a simple reason that it mentioned last time, probably. I don't remember. You see that if I have a Bose-Einstein distribution, n epsilon is positive. Is positive. So if mu would be positive as well, then for all epsilon between 0 and mu, this function would be negative. You see, if this is n of epsilon, then for all epsilon between E and mu, you would have that n of epsilon is smaller than 0. But it doesn't make any physical sense. You cannot have a negative occupation of a level, right?
But this depends on epsilon. If epsilon was not, if epsilon was less.
That's right. So that's what I said at the beginning. The fact that so if epsilon is a function that lives in a certain band, let's say lives in between, I don't know, minus j and plus infinity, let's say. Okay? Then in this case, your mu has to be smaller than minus j. It cannot enter the spectrum. Because if it enters the spectrum, you would have some modes that have negative occupation. And it doesn't make sense.
But the argument still holds.
The argument still holds. I mean, everything still holds. Actually, we will play around with this later on. But it still holds. So imagine, for example, you have like a metal made of bosons, which does not exist. But imagine that you have a band and you fill it up with bosons. And then what happens is that, so this band is going to have a band bottom and a band top, right? And then the chemical potential will grow and grow and grow until it reaches this. And then it cannot enter the spectrum, because if it would enter, all these modes here would have negative occupation. It's the same story. You see?
So, the density of states, G of epsilon, is square root of epsilon.
Yes.
And the density of states where energy is zero.
Yes.
But somehow, when we cross this critical temperature, particles still occupy that state.
Well, the
So
density of states is the number of states in a region d epsilon, right? So you don't get confused. What I'm saying is that they all occupy one quantum mechanical state, which is measure 0. If it's like when you pass from the discrete to the continuum. One state, right, like the ground state, has measure 0. So the contribution of one state in an integral is nothing, right? You see what I mean? Kind of. Anyway, think about it. The chemical potential cannot be positive. So if I would just solve this equation, I would get it positive. It cannot be. So it has to stay 0. But if it stays 0, then this number of particles is smaller than n, and the excess has to go somewhere.
It goes to the ground state.
It goes to the ground state.
So roughly, no.
We should make a noiseless projector. It makes such a noise. What? Everybody, each year we get, when we discuss Bose-Einstein condensation, everybody is, oh my gosh, what is happening? All students are confused by Bose-Einstein condensation. Don't worry, it will pass. Think about the question. I'll move on in the meantime, okay? All right. So everybody is sitting in the ground state. Now, what is important to notice is that it's not only that I have some particles that are sitting in the ground state, but I have a macroscopic number of particles that are sitting in the ground state. And this is crucial. Why a macroscopic number of particles? Because you see, Nx is written up here. You see that it's proportional to the density of states. But the density of states is proportional to the volume, right? And therefore, the number of particles in excited states is proportional to the volume. Of course, also n is extensive, is proportional to the volume itself. And therefore, if I take n minus nx and divide it by n and send the volume to infinity or n to infinity, I will get some finite number. You see? Because they all scale with the same power of the volume. In other words, when you have Bose-Einstein condensation below the critical temperature, the ground state starts being occupied not by one particle or by two particles, but by a macroscopic number of particles. And that's what they see experimentally. When they were first able to see Bose-Einstein condensation in optical traps, because before that it was not seen. When you see that, when they tell you that helium-4 is a manifestation of Bose-Einstein condensation, it's not true. Superfluidity happens in interacting systems and is due to phase stiffness. It's a different story. Bose-Einstein condensation in weakly interacting particles was seen for the first time in atoms trapped in optical traps around 95. I don't remember exactly. By Cornell et al. They got a Nobel Prize around that time. And so what they saw was that so they were lowering the temperature. Let's leave aside how they did it. But then at some point they were seeing that all these particles were sitting, a great deal of these particles were sitting in the ground state, in the same quantum mechanical state, and the way they could see it was by measuring time-of-flight experiments and seeing that they were all displaying the same features. Okay? So all in the same quantum mechanical state. So that's what is important. Now, the number of particles that are sitting in the excited states has also a name in this business. So the number of particles that is in the ground state, which is num n minus nx, so this difference, is the number of particles in what is known as the condensate. The condensate is whoever is in the ground state. The other particles, these ones, is called the thermal fraction. Okay? Thermal fraction, because these are all the particles that live in thermally excited states. So what happens below the critical temperature is that the thermal fraction is not saturating the number of particles anymore, and the condensate, the ground state, starts being occupied macroscopically. Clear? Now, there is, however, an issue. In all this calculation, it is crucial, in all this business of Bose-Einstein condensation, it is crucial what is the density of states. Let me make an example. Consider, let us see what happens if we try to make a Bose-Einstein condensate in 2 dimensions. Now you can ask me, am I able to do Bose-Einstein condensation in 2 dimensions? Physically, yes, you're able to do that, for example, in optical traps. Okay? So let us play first the game of saying, okay, let us take a 2-dimensional free space and particles have the dispersion epsilon p equal to p squared over 2n in 2 dimensions. So now I want to play the same game as before. I want to fix n equal to integral d3p 1 over e to the beta epsilon p minus 1. And I want to find what is the temperature at which this equation is satisfied. In other words, what is the temperature at which I get zero chemical potential. Okay? So let us see. Let us make a change of variables. 0 plus infinity. And by the way, I have v over h cubed. So v over h cubed, dp. 9, I don't have p squared, I have p. And then 1 over e to the beta epsilon p minus 1. Epsilon p is the usual p squared over 2m. Now I make another change of variables. I call beta p squared over 2m, I call it x. And then dp, if you do the calculation, comes out to be square root of m over 2 beta x dx. And this is equal to, and then if you make this change of variables, you get that this is, sorry, I made a mistake here. No, I'm in 2 dimensions, not in 3 dimensions. So this is area divided by h squared. So I make the change of variables.
I don't see what happened from the first step to the next one.
From where? From here to here?
Yes. From the 3p to dp.
Well, because it's not a D3P, it's a D2P. It's a D2P. Sorry.
And we need 2 pi or something like that.
And we need a 2 pi. That's also correct. That was going too fast. So this is what you are not supposed to do in the final exam. Going too fast. All right. You still don't see what? Well, if you go to polar coordinates, right, in 2 dimensions, then integral px dpy is equal to integral dp p times 2 pi for a spherically symmetric function. So now we see the light. Okay, so let's move on. Well, you do this change of variables, you insert it in here, and what you see is a over h squared times 2 pi times integral between 0 and plus infinity. Okay, I'll spare you the calculation. It's not difficult, but you will have dx m over beta 1 over e to the x minus 1. So in other words, this is equal to 2 pi a over h squared m over beta, and then integral between 0 and plus infinity dx 1 over e to the x minus 1. And now we have a problem. What is the problem? This integral is not convergent, it's divergent, which means that, what does it mean physically?
The assumption that chemical potential is 0 form.
The chemical potential in 2 dimensions is never going to hit 0. It's always going to be negative at all temperatures. And therefore, in 2 dimensions, there is no Bose-Einstein condensation whatsoever. Okay?
But you just said it's possible.
But it's possible. So how comes that in experiments they do see Bose-Einstein condensation, but it's impossible? There is one ingredient in the experiments that is very important. Experiments are not done in free space because free space does not exist. Experiments are done in optical traps. And all these details are extremely important for Bose-Einstein condensation. So now what I'm going to show you is that if you repeat the same game in an optical trap, then you are going to see Bose-Einstein condensation even in 2 dimensions. Okay? So how do we prove this? Well, suppose that you have...
So you mean that dispersion, like in optical traps, dispersion is not p-squared?
It's not p-squared. And this is important. It's very important. Because it's the divergence as small energies of this thing that is going to determine whether Bose-Einstein is the divergence, is the behavior of the density of states at small energies that determines whether Bose-Einstein condensation is seen or not seen. So if you do the calculation of the density of states for a 2-dimensional free gas, you will see that the density of states is just constant. And therefore, you see that everything is determined by this factor that is diverging. Now, if I want to see it also in 2 dimensions, I should use a density of states which is not constant at small energies. And this is exactly what is happening when you put it in a 2-dimensional trap. At small energies, the density of states actually goes like epsilon squared, as we will calculate in a second. And this is what makes the phenomenon observable in and in 2 dimensions, in a physical system. Okay? So, the way to do this is the following. So, I have a system that is sitting in an optical trap, and the potential is omega 1 squared x squared plus omega 2 squared y squared. Let's see. Okay? So, if this is the potential, then we know what is the spectrum of this system. It's a system of free particles. The spectrum is going to be determined by 2 quantum numbers, n1 and n2, and it's going to be given by h bar omega 1 n1 plus 1/2 plus h bar omega 2 times n2 plus 1/2. Okay?
This 1/2 will save the situation.
No, it's not. You will not be saved by a 1/2. I'm sorry. The 1/2 is just a constant. It's like the question he was asking before, right? I mean,
the density of states.
in this case, what is going to happen is that the density of states is going to start from the 0 point energy, right? So it's not going to start from 0. The minimum energy is h bar omega 1 plus omega 2 divided by 2. So this is the minimum energy, the energy of the ground state. So what you want is that the chemical potential hits this minimum energy. But when it hits this minimum energy, then you will still have the same problems as before. All right. So now, what I have to do is the following. You can imagine that if I want to solve the equation, so these n's are n1 and n2. If I start solving this equation to find the critical temperature, right? So I can now, I could try to write this as in the continuum. I mean, I can try to pass through energy and write it as an integral over energy, integral 0 and plus infinity, d epsilon, g of epsilon, 1 over e to the beta epsilon minus 1, where this is the density of states of this particular dispersion.
Here the chemical potential has been set to 0.
Yeah, sorry. You're absolutely right. Let us play the following game. Let us forget about the 0 point energy and subtract it. Okay? And therefore we set the chemical potential to 0. We understand that we should set it equal to the 0 point energy, but it's just a constant. Okay, so let us subtract the 0 point energy from now on. I'll write it here. So I'll write it in a nice form. We could not care the least for the 0-point energy. Subtract. Okay, this way you will remember that we subtract. Alright, so let us now move on. We have to find this density of states. How do we find it? So we do the following. G of epsilon, the density of states, is the derivative with respect to epsilon of G, big G of epsilon, where G of epsilon big is the number of states with energy smaller than epsilon. Okay? So now the trick is the following. So this number of states with energy smaller than epsilon, you can write it as follows. G of epsilon, you pass to the continuum limit, you would have a sum over n1 and n2. You write it as an integral dn1 integral dn2 of a theta function epsilon minus h bar omega 1 plus h bar omega 1 n1 minus h bar omega 2 n2. And now if you change variables and call epsilon 1 equal to h bar omega 1 and 1 and epsilon 2 similarly, okay, then you will be able to rewrite this as 1 over h bar squared omega 1 omega 2 integral between integral d epsilon 1 d epsilon 2 theta of epsilon minus epsilon 1 minus epsilon 2. Okay? And now this is equal to 1 over h bar squared omega 1 omega 2 integral between 0 and epsilon d epsilon 1 integral between 0 and epsilon minus epsilon 1 d epsilon 2. I mean, it's very simple to get it. So you perform the first integral. This is 1 over h squared omega 1 omega 2 integral d0 epsilon d epsilon 1, and then you have epsilon minus epsilon 1. Then you perform the second integral, and you get epsilon squared divided by 2h bar squared omega 1 omega 2. So this is big G, and then small g is just a derivative. So it's epsilon divided by h bar squared omega 1 omega 2. Now this is great because it means that, so before we had a constant density of states, now we have a linearly decreasing density of states, and therefore if we take n equal to integral between 0 and plus infinity d epsilon, g of epsilon 1 over e to the beta epsilon minus 1, well, you see immediately that the integral is going to be convergent, right? If you expand at small energies. And in particular, if you do a quick calculation, you will get that this is, so you have to set beta epsilon equal to x, and then you will get that this is equal to t squared over h bar squared omega 1 omega 2 integral between 0 and plus infinity dx x divided by e to the x minus 1. This integral here is pi squared over 6, and therefore we get t squared over h bar squared omega 1 omega 2 pi squared over 6. So from this you can easily find Tc, and Tc is finite. So that's why in 2 dimensions we could see Bose-Einstein condensation. So let's now play a game. I'm going to ask you, so you will need to do some calculations. Okay? So the game is the following. Suppose that now you are curious and we have a system that has this dispersion in 2 dimensions. It's just photons, and it's a linear dispersion relation in 2 dimensions. And the question is, will I have Bose-Einstein condensation or not? So let us see how you address this question, if you understood how to get this answer. See, do you want the dispersion? You haven't seen it?
Not the dispersion, the number of particles.
Number of particles is here. Well, is, this one is good enough. So let's everybody do it. So it's not that the first one tells me, yes, no, everybody should do this exercise. This and the next one.
The next one?
Well, there's another. There's maybe another 2. I want you to. This is one of the possible exercises for final exams. One of the possible. Certainly one that came out a few years ago.
It is.
Wait, let us finish. Compute the critical temperature and do it precisely. Okay, good, very good. And now? is, okay, everybody, P is more, no, but P is a vector, so it's always constrained between 0 plus infinity, cannot be predicted. And this P is the modulus of the vector. Right, so, yeah. So now, from here to here, okay, we go on. Finished. Do it in any dimension for this dispersion. Since you finished so fast. Pick up any dimension.
The same dispersion?
Same dispersion, but in general dimension. You figure out what is the dimension at which you start not having Bose-Einstein condensation. Don't. The moment you pass to spherical coordinates, and this is just a number, it's the modulus, right? So you don't have to rewrite it as px squared plus py squared. You see?
But I have to find the p, which is...
No, but I mean, this is the modulus, so what is epsilon p? Is going to be c times p, because p is the modulus of the vector. Right?
Yeah.
So you just have to substitute here c times p and change variables in this interval. Epsilon p. Okay, that's linear progress. Okay, now, so what is the conclusion? Is there or isn't there Bose-Einstein condensation? You finished? Okay, do it for a general dispersion.
Oh, come on.
So do it for this. A general dispersion P to the alpha. P is the absolute value.
In general dimension.
And not do it in general dimension. And don't do it too fast, otherwise I'll give you something more complicated. Sorry. So yeah, that's okay. So now. So is there or isn't there Bose-Einstein condensation? Since this is convergent, then is there or isn't there? No, why not? Yes, you can find the critical temperature, right? Whatever you say. So this is the equation to find the critical temperature. The fact that this interval is convergent means that this equation has a solution, and therefore there is a critical temperature. This happens. So I think what I'm going to do for the next two lectures is that we're always going to spend half an hour doing exercises at the end. I see that you need to do a lot of exercises. over 6. And where's the temperature here? Beta. Yeah, so you can find the critical temperature, which means that the risk of reaction to this section is very good. It's correct. No, I mean, it's much simpler than this. So the moment, so you see this, so this epsilon p is beta times sigma speed, right? So this is equal to a over h squared e to the 1 pp. No, you could write it as b times e to the beta minus 1. Now you change variables, right? You set beta cp equal to x, as you were doing correctly. So then what you get is a over h squared 1 over beta c squared times integral dx x over e to the x minus 1. You see? And now the question is, well, is this integral convergent or not? Is it? Sometimes. Is it convergent or not? It should be. Well, it is. So it is convergent. Why? Because in this integral, if you want to determine convergence, you just have to look at the Taylor expansion of the delineation. And you see that if the Taylor expand, it's 1 plus x plus x squared divided by 2 minus 1. But above you have an x. It cancels this one, so it goes to constant, it's minus. So therefore everything is fine, it's convergent.
Alpha derivation
You're doing it for general alpha as well?
well, already got the division one with this one, but this for the alpha, I have one for the alpha dimensional one.
I know, wait a second, don't mess up things. One thing is the dispersion, another thing is the dimension. So the dispersion, that alpha is not the dimension, it's the power of the dispersion. You're considering it as the dimension. Okay. Okay guys, let me show you how to do this. Hopefully. Or maybe let him show you how to do this. So why don't you come to the blackboard and explain how you do it? For one. Because then I will give the other one to everybody. We have plenty of time. Blackboard. Blackboard only. And you're going to be recorded.
Oh no. Is it recording?
Yeah. It's recording the blackboard. It's
Maybe
recording you.
I'll do like this.
You're going to be famous all over the internet.
We are doing this linear dispersion in 2D.
In 2D, yes.
Okay, then we will have the area squared. Okay, since the dispersion is spherically symmetric, we can go from Cartesian to polar coordinates. EP, P1, beta, P minus 1. And since in this case the momentum is defined only in the positive region, then the dispersion can be written as this, like without the modulus sign. Now, if we take the alpha coefficient down there, then we have alpha a h squared 2 pi divided by alpha squared, integral from 0 to infinity b epsilon 1 beta epsilon minus 1 b extra beta here, beta squared here. This is 2 pi a alpha beta h squared 0 infinity d x, so whatever it is, 1 x minus 1, and this is convergent.
The integral is convergent. When the integral is convergent, you just solve for TC,
Yeah.
which is sitting there. That's it. You're done. Okay?
Yeah.
It's very simple in principle. But it's so simple that now you can play the following game that you already did, so I'll give you another exercise. So play the following game. Take a system in, what is this? Let us now consider the following question. Same question as this one. So I want a dispersion epsilon p equal to, well, we called it alpha, let's call it c, absolute value of p. This is the modulus of the vector, but in d dimensions, or d is a general dimensionality. Okay? And I want you to find in which dimension at which or below which there is no Bose-Einstein condensation. Is it clear? So you just have to play the same game as before in a generic dimensionality and figure out for this dispersion when you don't have Bose-Einstein condensation. Okay? So try to play the same game. And you do it for a three-dimensional oscillator, for three-dimensional harmonic potential, since you already did.
In what dispersion?
Harmonic potential.
The potential is harmonic and the dispersion is...
No, harmonic. I mean, a harmonic oscillator, like the thing we have done before,
Ah, okay.
in three dimensions. And if you do it too fast, I'll ask you to do it in general dimensions. Yeah, that's okay. So what is the dimension below which you don't have Bose-Einstein condensation? There is another as well.
Right. Sorry. How was the capital P defined?
is the number, sorry, is the
It was
number
integral
of
with
states below a certain epsilon.
So the number of dimensions, it is only the
Okay, since you're so fast now, as a price, we will do it for a general dispersion methods in the dimensions. We'll figure out. After this exercise is practically everything there is to know. Sorry? No, this is which dimension? 2 dimension. 3 dimension. Yeah, I do it in general dimensions. Not in 3 dimensions, in d dimensions. That's correct. In 3 dimensions you will have Bose-Einstein condensation. Yeah, you should do this interview.
and both of the epsilon z's start from 0.
Yeah, all starts from 0. Yeah, so what is the dimension of Pluto? This is what? The n is the number of dimensions. So what is the dimension at which you attack?
after n is equal to 2 divided by times.
No. Why? Think about, so this integral is always convergent for large x. What is divergent for small x? Why is it divergent for small x? For large x is always convergent. Why is it divergent for small x?
Only for n is equal to this or equal to 2.
No. Just expanding, bigger expansion of the denominator is what x. And above you have n minus 1. So is x to the n minus 1 minus 1. So it's n minus 2. X to the n minus 2. So when is this convergent? When is an integral of a power like this convergent with small x?
For n is equal to 2.
For n is equal to 2 is convergent. For n is equal to 1 it is not convergent because it's a logarithmic and divergent. 1 over x is not a convergent integral. It's logarithmic and divergent. This is correct. So what is the n for which? 1. Great. So, yes.
This heaviside function
Yes.
will terminate this integral from 0 to epsilon minus epsilon x minus epsilon y.
Yes.
And it will be just...
No, but then
there has to be something done with both these two.
For a second. I think this one should be constrained between 0 and epsilon, and this one should be constrained between
0 and epsilon
and
minus
epsilon minus
x.
epsilon
Yeah.
x.
Why I get that for general P alpha the dimension is still 1 in order for nothing to be.
Why do you get for general P outside the dimension is still 1? I think about the calculation, so we should explain it.
Since I have P minus 1 and now P I can write it as x as proportional to 1 over alpha.
So, wait a second. So what you have is dp, and you will have p to the d minus 1, and then you will have e to the beta, essentially p alpha minus 1. Then you take your expand dp, p to the d minus 1, and then you will have p to the alpha. And then you have p to the d minus 1 minus alpha. So I don't see why it is 1. You see? Why do you put something like why do you have an alpha in the denominator? Because you want to put it here as PC. Yeah, if you change variables, then you will get. This is your epsilon, but then you will have some powers of epsilon somewhere here, right? They cancel? No, it's okay. I mean, it might be correct. So what is this is 1 minus 1 over alpha. You have epsilon to the power n minus 1 in alpha, and then you have another epsilon in this. So you get an epsilon n minus 1 minus 1 minus 1 plus 1. So let's put everything together. So we get n minus 1. So from what I said from the argument that you have p to the n minus 1, and then if you take or expand the thing you will put p to the alpha. Right? Because this is e to the beta epsilon p minus 1, if you expand this beta epsilon p, so it's going to be p to the alpha. The convergence of this integral is determined by looking at n minus 1 minus alpha, right? And, just looking at this, I would have, when this is smaller or equal to 1, then the integral is divergent. Correct? No, I'm not taking the high temperature. I'm just looking at that convergence for, this integral here has a problem of convergence at small p. So I'm just looking at the convergence of the integral at small p. So if alpha is equal to 1, this tells you that n here has to be smaller than 1 in order to get this. You see? Because of alpha is equal to that. You see? You finished. Sorry? Yeah, I just have to check. Just 1 second.
I'm not quite sure if this pattern is correct for arbitrary.
No, it should be x squared.
Is this the dimension of this thing?
Most probably, yes.
So
I
then in
suspect.
one dimension it doesn't.
Yeah. Okay, guys, let me tell you what is the solution. So, you should understand by now one important thing. Whenever you want to solve this kind of problems, right, of determining whether you're so what you have to do is essentially the following. In d dimensions, you will have when you pass to the continuum, integral dp, and then 1 over e to the beta epsilon p minus 1. And you want to determine when this is. So the only thing you have to determine, roughly speaking, is when this integral is convergent or divergent. So since you have spherically symmetric dispersion, what you do is, you pass to spherical coordinates. So you have the solid angle in d dimensions, and then integral between 0 and plus infinity dp p to the power d minus 1, and then e to the beta epsilon p minus 1. Now, you might do the whole calculation to figure out what is the critical temperature itself. But already looking at this integral, you can see whether Bose-Einstein condensation is going to occur or not. Because you see that this integral here is an integral over p, and the only problem it can have is that epsilon p goes to 0 as p goes to 0. And therefore it might have what is known as an infrared divergence, a divergence for small momenta. But what you can do is, in order to estimate whether this infrared divergence is dangerous or not, you just expand. So you have p to the d minus 1 over e to the beta epsilon p minus 1, which is, for small p to the power d minus 1 times beta c times p, right? So is p to the power d minus 2 times beta c. Now, if you have an integral, if I give you an integral dp p to the power d minus 2, when is this integral convergent? For which d's is this integral convergent? So if I have an integral dx x to the alpha integral between 0 and blah blah blah, when is this integral convergent? For all alpha, no, not positive alpha.
Negative.
So for alpha equal 1, is it convergent? No, it's logarithmically divergent, which is known as a logarithmic divergence. So for alpha equal to 1 is not convergent. For alpha equal to 2, is it convergent? Is it convergent for alpha equal to 2? Is it convergent? I want a... Is it convergent for alpha equal to 2?
No.
No. Alpha equal to 3?
No.
No. Alpha equal to 1/2?
No.
Please. Alpha equal to 1/2.
Yes.
Yes.
Yeah.
For all alpha smaller than 1, this integral is convergent. Okay? You have to stick this in your mind. Alright? It's very important. Otherwise, you will never solve any exercise on this stuff. This integral is convergent for small x, where you have problems, for all alpha smaller than 1. Right? Well, for all alpha greater than 1 is divergent. It happens the other way around if you consider an integral like this, between some positive number and plus infinity, dx x to the alpha. This integral, when is it convergent? For alpha greater than 1. Okay, so just remember this. It's very easy and very simple, and it's very important. How do you prove it? You just do the integral, right? And you prove it. It's very simple. It's related to the fact that when you integrate the function 1 over x to the alpha, then the primitive is 1 over alpha minus alpha plus 1, no, minus 1, but whatever. Don't get me confused because of the sugar. So, anyway, that's the way it is. Alright, so we have d minus 2. For which dimensionality we will have? We are not going to get 1. Okay. So in one dimension, we are not going to get, in one dimension, you're not going to get, in one or below one dimension, you're not going to get Bose-Einstein condensation. And now you see that if I would generalize this exercise and put epsilon p equal to p to the alpha, well, then I can play the same game, right? I can put a p to the alpha here, and then I will get here, instead of minus 2, I will get minus 1 minus alpha, right? But still, the only thing I have to do in order to determine whether this integral is convergent or divergent is set this, so whenever this is smaller or equal than minus 1, then this integral is divergent. And then you solve this inequality and you have the final result. Okay? Great. So remember this. In order to figure out, you just have to remember the convergence of these integrals, and in order to figure out whether you will have or you will not have the Bose-Einstein condensation, it's important to know what is the behavior of your dispersion at small momenta. That's it. Okay? Good. So next time we will do the black body radiation. By the way, next week we are going to have a reshuffled schedule because you will have to learn Python. Okay? But essentially I'm going to follow more or less the same style as today. So since you haven't, I suspect that you haven't been doing enough exercises. So let us do 1 hour lecture and then do some practice. And then maybe we'll go back to previous topics and do some more practice on some previous topics. What? Thermodynamics, etc., etc. You will do it with me, with Silvia. We'll do practice. Okay?
Sorry, I have this stupid question, but do you frequently do numerics in your research?
Not frequently. Why?
Every once in a while?
Sometimes. Why?
What kind of numerics?
Simple one.
I hate it and I'm really bad at it, and I just want to know how important will it be.
How important? It depends what kind of physics you do. Right? I mean, it's important to know it.
Of course, about numerical stuff. I will definitely not be.
No, come on. Don't be lazy. You have to learn it. Right? You're a student, you have to learn it. Then, maybe you can forget it. But you have to learn it. I mean, I took an exam in general relativity when I was a student. You think I'm doing general relativity?
When are we going to have the
What was it? The exam?
Yeah.
The final one or the fake one?
The fake one.
The fake one we said we were going to do it in the first week of December. Is that okay?
Yeah, I think yes.
Yeah, because the second week we are done. I mean, it's over, of course. And then you have a month, and then on 8th of January, 7th of January, you can do it. So, come back from vacation. Oh, I forgot. Sorry, I've been sick. It's not only I've been sick. I've been sick myself, my wife, and 5 kids. So it has been a major disaster. So, I'll get back to the recommendation.